You are welcome in this new talk in our Applied Mathematics webinar. Our speaker today is Hassine Maatoug from the Laboratory of Analysis and Control of Partial Differential Equations from the Science College of Monastir. Hassine Maatoug defended the thesis in 2003, and he works on mathematical modeling and numerical simulation of dynamic aeration under the supervision of Professor Mohamed Jawa, and with the collaboration with Fadi Daberi and Mohamed Amara from Riyad Kankour. And in 2008, he defended the habilitation, and the title of the research was Topological Sensitivity Analysis Method, Theory and Applications. Hassine Maatoug was a lecturer at the Faculty of Science 1999, and he became assistant and between 2000 or 2004, and assistant professor from 2005 to 2010, and a professor from 2015. He supervised 10 theses, including 2 under joint supervision, and he published more than 50 papers. The research areas of Hassine Maatoug is mathematical modeling, numerical analysis, inverse problems, topology, and shape optimization, fractional calculus, and fluid mechanics. And the talk today is around the topological sensitivity analysis for the 3D nonlinear Navier-Stokes operator and applications in the frame of collaboration with Ali Harzallah from l'INSTM at Monastir. Thank you, Hassine, for accepting our invitation. And you have around 45 to 50 minutes for your talk.
Okay, thank you very much, Nabil. Thank you, Rafiq. My talk is about topological sensitivity analysis for the 3-dimensional Navier-Stokes operator and application. It is a joint work with Mourad Harizi, Rakia Malik, Marwa Aouni, Sana Shaush from the Monastir University, and the Professor Ali Harzallah from l'Institut National des Sciences et Techniques de la Mer de Monastir. Okay, donc in this work, we consider a viscous and incompressible fluid flow in a bounded and smooth 3-dimensional domain. We assume that the fluid flow is governed by the full nonlinear Navier-Stokes equations, and we assume that the fluid flow domain contains a finite number of rigid bodies. We will call it by obstacles, and we assume that well separated but not close to the boundary. Our aim in this work is to localize and identify the unknown obstacles from boundary measurement of the velocity field. So this inverse problem can be formulated as follows. For a given measured velocity field on the accessible part of the boundary, we aim to detect the location and reconstruct the shape of the unknown obstacles from the accessible surface in such a way that the velocity and pressure fields satisfy this overdetermined Navier-Stokes system. The main difficulties here The first difficulty comes from the ill-posedness of the problem. So this problem is highly ill-posed in the sense of Adama. The ill-posedness comes from the instability of the problem. Also, the classical identification approach need more a priori information about the obstacle's location because they dependent on the initial guess. They also need appropriate regularization technique for overcoming the ill-posedness. On the other hand, the topological gradient method, which has enjoyed important success over the last decade, is limited to the linear operators. So in this work, we will solve this geometrical inverse problem to solve this problem, we will proceed in two main steps. And the first one, we will extend the topological sensitivity notion to the nonlinear case. We will derive a topological sensitivity analysis for the full nonlinear Navier-Stokes operator. And the second step, we will perform a detection approach combining the convolvulation formulation and the topological gradient method. So using the convolvulation formulation, the inverse problem leads to define for any admissible obstacles two forward problems. The first one is called Newman problem. It is related to the Newman boundary condition. The second problem is called Dirichlet problem. It is related to the given Dirichlet boundary condition on the accessible surface. So using this concept, the geometrical inverse problem can be formulated as a topology optimization one, where the unknown obstacles domain will be characterized as solution to a topology optimization problem, minimizing a shape function which measuring the misfit between Newman and Dirichlet solutions. So to solve this topology optimization problem, we will develop an approach based on the topological gradient method. So the main idea of this technique is it consisted in studying the variation of the design function with respect to the creation of a small hole inside the computational domain. It is to an scientific expansion of this form, where rho epsilon is a scalar positive function goes to 0 with epsilon. However, the function delta G, which called topological gradient, play a crucial role in our detection approach. And it will be used for detecting and for localizing the obstacles domain and approximated its shape. So the rest of this talk is organized as follows. In the first part, we will develop a topological sensitivity analysis for the full nonlinear operator. Then we will develop a topological gradient-based approach for solving the inverse problem. In the third part, we will develop an application and we will use our detection approach for identifying rigid body immersed in the Mediterranean Sea. And we end with some conclusion and prospects. So for the topological sensitivity analysis for the full nonlinear Navier-Stokes equation, we will study the variation of the velocity field with respect to the presence of small obstacles inside the fluid flow domain. So the perturbed velocity and pressure field satisfy this perturbed Navier-Stokes system. And our aim in the first part of this section, we will evaluate the asymptotic behavior of the perturbed velocity field with respect to the perturbation size. So we will prove that the leading term of the velocity field variation will be defined by this expression, where say J solves this Stokes exterior problem. And we'll derive this theorem, which we will prove that there exists a positive constant independent of epsilon, such that the variation u epsilon minus u0 minus the leading term minus the leading term with the norm L infinity 0t L2 plus the L2 0t H1 norm less or equal a constant C times epsilon. So to prove this result, we will start by intrinsic sum notation. We will note by or epsilon the variation of the velocity variation and par S epsilon the pressure variation. It is easy to see that the couple R epsilon S epsilon solve this nonlinear Navier-Stokes type problem, where u epsilon is defined by this expression. Okay. Sorry. The search term here are defined by this expression. And the aim is to prove that there exists a positive constant C independent of epsilon, such thing that estimate. The main difficulty here is that the constant provided by classical energy estimate depend on the computational domain, which depends on epsilon. To overcome this difficulty, we will decompose the solution in three main terms. The first term is related to the boundary condition imposed on the obstacle boundary. The second term will be chosen, will be constructed by this formula, where gamma G is solution is satisfied this stationary Navier-Stokes Stokes problem and depends on the boundary condition imposed on the exterior boundary. The third term is chosen such that the variation, the velocity variation satisfy that R epsilon equal to R1 plus R2 plus R3. And it is easy to see that the three terms satisfy this Navier-Stokes type equation, where the convection term psi epsilon is defined by this expression. And the third term here are defined by this expression. After the decomposition of the velocity field variation, we will examine each term. We will determine the behavior for each term separately. So for the first term, we will establish that there exists a positive constant C independent of epsilon, such that the L infinity 0 T L2 plus norm plus L20T H1 norm less than or equal to C times epsilon. Now, for the proof of this result, we will use a variational technique. The main idea here is to reconstruct an appropriate test function defined by this expression, where U epsilon satisfies this Stokes system problem, which is defined in a fixed domain independent of epsilon. The main properties of this test function, but it consists with the term R1 epsilon and the obstacle bounded. And it has an explicit behavior with respect to epsilon. So using the weak formulation of the Stokes problem satisfied by R1 epsilon, one can deduce that the term R1 epsilon satisfies that equality. So by variation inequality, one can deduce the estimate for the first term. Now we consider for second term, which is defined by this expression, where gamma g, theta g solve this stationary Stokes problem. We will use this preliminary. We will prove that there exists a positive constancy independent of epsilon, such that the norm, the L infinity 0T L2 plus L2 0T H1 norm less than equal to C times epsilon. To prove this result, we will use the preliminary lemma, which provides the behavior of the exterior Stokes problem solution with respect to epsilon. Such estimate can be derived with the help of a single potential layer. So for the third term, similarly, we will prove the same estimate. We will prove that there exists a positive constant independent of epsilon, such that the norm L infinity 0T L2 plus L2 0T H1 norm less or equal than C times epsilon. The proof of this result is based on two steps. In the first step, we'll establish that there exists a positive constant independent of epsilon, such that the zero norm is less or equal to this sum. And we will determine the behavior of each term with respect to epsilon. To determine the behavior of the term G K epsilon with respect to epsilon, we will use some preliminary result concerning the nonlinear term. Okay, with this result, we end the proof of our first theorem. So we start our second part, where we aim to derive an asymptotic expansion of the considered design function. So in this part, we will derive a general mathematical framework which valid for all cost function f epsilon satisfying the value of this estimate, this assumption. We assume that f0 is differentiable in H1, and we assume that there exists a scalar function that the variation of f minus f0 satisfies that asymptotic behavior. Also, we assume that the H1 problem has unique solution on the Hilbert space H1 omega. As a first step of our analysis, we will prove a preliminary result, preliminary estimate for the design function variation. We will prove that the variation of the design function with respect to the insertion of small obstacles inside the fluid flow domain satisfy this equality, where T1, T2, T3 are termed to be evaluated with respect to epsilon. So using the obtained estimate for the velocity field variation, we prove that for all cost design functions satisfying the assumption admit this asymptotic behavior, and the topological gradient is defined by this expression, where U0 is the velocity field solution to the non-perturbed Navier-Stokes problem. V0 is the solution to the associated adjustment state. However, the tensor TO is called the visco moment tensor, which modeling the obstacle shape effect. It is defined by this expression, where eta is the solution to this boundary integral equation. So here the topological gradient is defined by an implicit formula, and where the visco moment tensor is known implicitly. To get a more explicit expression, we will consider some particular shape, particularly for spherical shaped obstacle. The visco moment tensor is known explicitly, and we obtain this asymptotic, a more explicit asymptotic expansion. So we will prove that for a small spherical shaped obstacle, the variation of the design function satisfies this asymptotic expansion. The delta F is in this term, the delta F represents the influence of the expression of the considered shape function. So we'll present here two standard examples of cost function that satisfy the assumption R. A. The first example is concerned with the L2 norm. So for this example, we prove that this function satisfies the considered assumption with delta F, the variation delta F is equal to 0. However, for the seminorm function, we will prove that this function satisfies the assumption R, but for a variation defined by this expression. So we will use this the developed theoretical analysis for developing a topological gradient-based approach for identifying the emergent obstacle. So to solve our considered inverse problem, we will use, as mentioned in the introduction, we will use the convolvulus concept. So where the unknown obstacle domain will be characterized as the solution to a topological optimization problem, where the shape function measures the misfit between the Newman and Dirichlet problem. To solve this topology optimization problem, we will derive the topological sensitivity analysis for this convolvulus type function. In the presence of a small obstacle, this design function is defined by this expression, where u and epsilon is solution to this Navier-Stokes problem with a Newman boundary condition on the accessible surface. However, the u epsilon d satisfies the Navier-Stokes equation with a Dirichlet condition on the accessible boundary. By an application of the mathematical framework developed in the first part, the variation of the convolvulus function satisfied that can be decomposed in three main terms. The first one is related to the Newman of the velocity field solution to the Newman perturbed Navier-Stokes problem. And the second term is dependence on the u epsilon d, which is solution to the Navier-Stokes, perturbed Navier-Stokes Dirichlet problem. However, the third term is dependence on, it is a mixed term, depends on u and epsilon and on the Dirichlet and Newman solution. Also, we will apply the mathematical framework. One can prove that there exists a positive constant independent of epsilon, that the velocity field variation satisfies this estimate for both the Newman and Dirichlet perturbed problem. And you think the general developed case, one can deduce that the convolvulus function satisfies this asymptotic expansion, where delta k is the topological gradient associated with the convolvulus function defined by this expression, where u n0 and u d0 solve the non-perturbed Navier-Stokes problem. T and TO is the visco moment tensor, which is defined by this expression, where u0n and u0d are the adjoint state solution to the following systems. Similarly to the previous case, if we want to get a more explicit expression for the topological gradient, we consider spherical shaped obstacle, and in this case, the topological gradient is defined by this expression, an explicit expression depend only on the u and epsilon and v and epsilon is the solution to the Navier-Stokes Newman Navier-Stokes problem in the non-perturbed domain and its associated adjoint problem, and the Dirichlet and the solution of the Dirichlet Navier-Stokes problem in the non-perturbed domain and its associated adjoint problem solution. So, using this topological gradient, we will develop a numerical identification algorithm based on the following steps. In the first step, we need to solve the Newman and Dirichlet Navier-Stokes problem and compute the velocity field un0 and ud0. In the second step, we need to solve the associated adjoint problems and compute the adjoint state un0 and ud0. In the third step, we compute the topological gradient at each point x of the computational domain. The unknown domain will be constructed by this, will be approximated by this set of points that x in the computational domain, that the topological gradient is little than or less rho star delta mean, where delta mean is the most negative value of the topological gradient in omega. Rho star is obtained by minimizing the scalar function with respect over the interval 0, 1. So the location of the obstacle location will be detected by the most negative value of the topological gradient. However, the shape of the obstacle shape will be approximated by the topological gradient level set curve. So we'll use this performed numerical approach for identifying some obstacles from velocity measurement, from measurement of the velocity on the accessible boundary. As a first application, we'll apply our developed numerical algorithm for identifying obstacle immersed in a cavity by the means of boundary measurement. The flow domain in this case is defined by a two-dimensional square cavity. The measurement pattern are synthetic that is generated by a numerical computation. So we present here some numerical results for a circular shaped obstacle, where the exact obstacle is plotted by black lines. As one can observe here, that the topological gradient detects the location and the shape of the unknown obstacle for different positions inside the cavity domain. The second test is here we test our algorithm for different obstacle size. The same test, we have used our numerical algorithm for identifying some elliptical shaped obstacle having different size. And we conclude here that our detection algorithm detects the size and the location of the unknown obstacle. In the third test, we will discuss the influence of the relative position of two obstacles. I will remark here that when the two obstacles are well separated, we have a good detection result. However, when the distance between the two obstacles decreases, the topological algorithm detects only the zone containing the two obstacles. In the fourth test, we have discussed the influence of the relative size. As one can observe here, that the detection algorithm can detect the biggest obstacle, and the relative size has an influence on the accuracy of the numerical algorithm. The last example is concerned with the detection of some obstacles defined by non-smooth domains. We remark here that our detection algorithm give a good detection of the location of the obstacles obstacle. However, the size is not well approximated by a level set curve of the topological gradient. The second application of this numerical approach, we use our numerical identification algorithm for identifying some rigid body immersed in the Mediterranean Sea from measurement of this surface velocity field. This work is in collaboration with Prof. Ali Harzala from l'Institut National des Sciences et Technologies de la Mer. In this example, we have applied our numerical identification approach for identifying a rigid body immersed inside the fluid flow inside the Mediterranean Sea. The exact location of the unknown rigid body is represented by this black square. Our detection is based on the measurement of the velocity field on the sea, on the surface of in the local zone of the surface of the sea. So, using our numerical detection algorithm, and we obtain this result. So here we plot the topological gradient ISO value in the computational domain. As one can remark here, that the most negative value of the topological gradient coincides with the exact position location of the unknown obstacle. So we have a good detection of the unknown obstacles from a measurement of the velocity on the surface, on the sea surface. In the second example, we aim to detect two obstacles, two well-separated obstacles. We present here the location of the exact unknown obstacle. So, with our numerical detection process, we obtain this ISO value of the topological gradient where the most negative value coincides with the exact location. So we have a good detection of the obstacle location. And the last example, we will discuss the influence of the interaction between the two obstacles on the accuracy of the detection process. So, with our numerical detection process, the topological gradient, the ISO value of the topological gradient has this ISO value representation. So here we remark that the topological gradient detect only the zone where containing the two obstacles. This is the interaction between the two obstacles. So in this work, we have developed a topological asymptotic expansion for the full nonlinear Navier-Stokes operator, which valid for a large class of shape function and arbitrary shape geometric perturbation. The mathematical analysis is general and can be adapted for other partial differential equations. Also, we have performed a fast and accurate numerical algorithm for identifying the emergent rigid object inside the Mediterranean Sea. As prospects, one can derive some theoretical results study related to the identifiability and stability question. Also, one can derive a convergence result for the numerical algorithm. Another interesting problem is the development of an identification process based on the sequential satellite images. More precisely, it consisted in developing identification process based on sequential satellite images. For this question, the identification process will be based in two main steps. In the first step, is concerned with the identification of the sea surface velocity from sequential satellite images. The second step will be concerned with the identification of the rigid body from the sea surface velocity. So for the first step, there are many approach has been developed in the literature. I can cite the approach which is based on satellite thermal images and simplified ocean circulation model. Also, one can use the approach based on neural network and thermal image treatment. Also, I suggest another approach which is based on image registration from the help of high order topological gradient for geometric feature extraction. This last approach with this approach one can reconstruct the velocity field in the sea surface and use the result for obstacle identification by using the topological algorithm. However, for the second step, the data will be proceed with an identification of process, but with poorly information measurement. So in this case, several mathematical issues of high interest need to be discussed since the measured data is now approximated. Particularly, the constructed velocity in the sea surface will be not divergence. The divergence of this velocity is not equal to 0, which pose some difficulty in the analysis. And thank you for your attention.
Thank you, Maatoug, for this nice talk. Are there some questions, please? I have a very good question, Professor Maatoug, please. Why do you insist on the Mediterranean Sea? These techniques are not applicable for any sea. In your talk, you insist that you are interested in the Mediterranean Sea. Your techniques are not applicable for any other sea. What is the specificity of the Mediterranean Sea? You understand my question? Okay.
Okay. First, I'm sorry for my bad English.
No, it is okay, Maatoug.
French English action. So we have concerned with the Mediterranean Sea because we have some result from the Institut National. We have a numerical solver. We have used the numerical solver of the Institut National of Science Technology de la Mer, which they have an European Mediterranean project in this subject.
Okay.
And we have some real measured data in this.
Okay, because you have some data.
Yes,
for the
real
Mediterranean Sea.
measured data. We accept some real measured data.
Okay. I have another naive question also. Can your techniques be adapted to track obstacles in case where they move?
Sorry,
I mean that if we assume that we know by one means or another the nature of movement of these obstacles, are your techniques can be adapted to this problem?
It is an interesting question.
Not random movement, movement what is which is deterministically,
yes,
not random.
Yes. It is an interesting question, but the actual the developed approach, the actual result we have a result for stationary fixed position for the obstacles.
Okay.
But we have some work, but not finished, but in the moved obstacles.
Okay. Okay. Thank you. Are there other questions, please?
I have some questions, please.
Yes, Mohammed.
Okay, thank you, Maatoug, for this nice talk. The developed formula is very interesting because it is very technical and difficult. It is valid in three dimensions, I think. Yeah. Do you have some numerical result in 3D? Some tests in 3D applications?
Yeah, in the case of the Mediterranean is in 3D. It's not real with using real measurement.
But you integrate. You suppose that it is a shallow flow. It means
the domain is.
It is not 3D. It is approximatively
integrate with respect to the vertical direction.
Okay.
But the solver has been validated using real results and compared with the Copernicus real measured data, the European measured data for the numerical simulation of the water simulation.
Okay.
For the water simulation, the motion of the water and the wave and the temperature and salinity has been validated with some exact result measurement.
And the model is incompressible or compressible?
Incompressible.
Do you think that you can generalize this result for compressible flows with variable density, etc.?
No, it is very difficult. Maybe it is possible, but it is very difficult. And because
you don't have the same equations. The divergence U is not equal 0, then you have other equations.
Why it is possible, but it is very difficult to do.
Okay. And for your applications, the body that you found, the size is small that you can use this
The
development
relative
formula?
size will be small with because we have a domain which domain size of the 300 kilometers by 700 kilometers. So every
Then you can consider.
obstacles will be small, relatively small in the domain.
Okay. Okay, thank you, Professor Maatoug, for your nice talk.
Thank you.
Other questions, please?
I have a question.
Yes, Professor.
Thank you for nice talk. My question is about numerical simulation, about obstacle. You make obstacle or obstacle is naturally here to detect it? Thank you.
Sorry, you?
Obstacle.
Yes. Numerical simulation.
Yeah.
If you who makes obstacle or you see obstacle naturally?
For the to get measurement data, we take an obstacle inside the fluid flow domain, and we get the synthetic measurement by computation for the academic, for the first example. For the application of the detection for Mediterranean, we have used the artificial obstacle inside the domain, and we have used because the direct solver used some real measurement and the combination by simulation and real measurement of the fluid flow dynamic. Okay.
Okay. Thank you. And I see. And my last question is why why about your choice using also Neumann condition and Dirichlet condition? Why not only condition? Why to either? Why are you using the same and Dirichlet condition?
Generally,
in the calculation, you use also Neumann condition and Dirichlet condition.
Yeah. Generally,
Okay.
in geometric inverse problem, non-inverse problem, we impose a Neumann condition on the surface, and we measure the response of the dot. So the measured velocity here will be where we have the information on the obstacle locations. As in many other problem applications, like in structure, we impose a force on the structure and we measure the velocity, the displacement. So we need overdetermined data to reconstruct the unknown geometry domain. We need an overdetermined data to reconstruct the unknown part of the geometry domain.
Okay. Okay. Thank you. Thanks a lot. Thanks for nice talk.
Thank you for you, Professor Mohamedou. Are there other questions?
Yes, Rafiq.
Yes, Nabil.
What is the application with the NSTM, Hassine?
The NSTM, they developed the numerical solver for the simulation of the of the dynamic motion Mediterranean Sea, as well as the dynamic of wave, as well the temperature distribution of the Mediterranean Sea. They have coupled solver that simulate temperature as salinity, velocity, wave motion, and use the solver for simulate the of the pollution source.
Then the obstacles are the pollution sources in their application?
No, the obstacles is our applications, but they not use the obstacles in their work, but in their work they use the direct solver for simulate pollution and the distribution of temperature, salinity, and many fluid parameters.
Okay,
and,
I understand.
Just for they use just the direct problem.
Okay, in fact, the collaboration is that you use their solver for your inverse
The
problem.
way, yes, and that's yes.
Okay.
But they interested by this application for other applications are they have a project about wall pollution, and they want to localize the source.
Okay, but in the beginning of your talk, you said that the topological gradient is used when for linear operators, but in this case, the problem is nonlinear. Then what is how you introduce then a new method, or how you solve this problem of nonlinearity in this case?
Fact, and the beginning of my talk, I said that existing approach based on topological gradient are limited to the linear case. In this work, we have generalized the extended topological sensitivity notion for the nonlinear case. And our main tools, we have used some interesting inequality proved by Giovanni Galdi in their work. Like, we have this inequality. So we have used some interesting inequality to develop, to extend the topological sensitivity notion for the nonlinear case. We have used some inequality where for example, in the 3 point here, there is a constant of the inequality depend explicitly with respect to the domain, where we can prove that this constant is uniformly bounded with respect to epsilon.
Okay, thank you.
I have just a more general question, Professor Maatoug, please. My question is, it is naturally to interest to the following problem. The problem is to make some estimation about the time location of the obstacle if we suppose that it moves randomly. Your obstacle is not fixed, but it moves at random. It is this problem interesting or not, to make some estimation about the time location of the obstacle? For every time t, we need to have some information about the location of this obstacle.
Yes, it is an interesting extension, but we are interested in this question for theoretical case. Like we have, we want to develop some similar estimates for moved geometric perturbation.
Okay. Thank you for you. Other questions, please? Are there other questions? If no, we have to thank again Professor Maatoug Hassine for this nice talk and this nice topic. And
Okay, thank you very much. Thank you, Raquel. Thank you, Nabil. Mohammed.
Thank you, Maatoug.
Thank you for this talk.
You happy?
And we stop here and see you after 2 weeks, 21
Thank you.
November. Thank you.
Thank you very much.
Okay, see you.